we're going to pick things up right where we left off on Friday's lecture, except we're not going to go deeper into the quantum realm. All right, I brought you to the brink, and then I'm going to pull you back into safety. Okay, but Friday's lecture was informative, I hope, to help at least give you some insight as to why we then follow the rules and conventions that we're going to start learning about today. And these conventions are how we describe electrons in atoms in their most stablest configuration. Everything that we do in this class is really driven towards stability. The things we describe are reactions that might take place happen because the products are going to be more stable. The things we describe are in their most stable place. That's what we call the ground state, right? The least amount of energy that you need to supply to the system to keep things the way we're describing them, right? So that's kind of an overriding theme here, right? Most stable, right? The least amount of energy needed to keep things as we're describing them. That's the overriding theme here. Now, I left this slide up from the last time because also going over all of that quantum theory and the quantum model of how the atom is organized and the electrons are organized within the atom explains why the periodic table has this funny shape. So I'll be going back to this idea about the S blocks and the P blocks and the D blocks probably a few more times this week. To emphasize what we went over the last time. So I'm not going to do that again now. I'm just going to remind you that this shape is based on how the electrons are organized in the quantum mechanical model of the atom. All right, but we're going to learn about a couple of other ways that we're going to notate electrons in atoms. These are probably going to be ways that are more familiar to you if you had a high school chemistry class or another chemistry class recently. And that has to do with using orbital diagrams and electron configurations. And as we're doing that, I'm going to be highlighting these three principles or rules. The Aufbau principle, and I'll just introduce these to you now. The Aufbau principle, this is just the order of filling. Aufbau is German for building up. So really, Aufbau principle, it's not somebody's name, it's just a German word. This principle is that as we add more and more electrons to an atom, since we're trying to describe the most stablest configuration, we're going to start at the ground floor, the ground state, and we're going to work our way up. So as we add more and more electrons, we're going to add them to the next highest energy level that's available. Okay, so we're going from the lowest energy to the highest energy level. Hund's rule and Pauli exclusion principle, I'll go back to those when we get to them in our description of orbital diagrams and electron configurations. So, well, actually, Pauli exclusion principle we already talked about a little bit on Friday. That was the idea that you can't have two electrons at the same place at the same time, even though we can't ever see exactly where they are. Remember, this is now all probability. We can at least posit that wherever they are, they can't be at the same place at the same time. And given that there's evidence for two electrons within a given orbital, but they can't occupy the same space. At the same time. So we think of them as their magnetic spins, one and in opposite direction. So we're going to call one spin up. We're going to use an up arrow for that. And we call the other one spin down. And we'll use a down arrow in our model for that. And I'll come back and fill in Hund's rule in a minute. So first, let's talk about orbital diagrams. So you have to remember what an orbital is. We defined what an orbital was in last lecture. It's this probability. It's the square of the waveform, psi squared. Remember that. And it defines the probabilistic space where those two electrons at that particular energy level in that orbital can be found. And so we're going to use boxes for our orbital diagrams. And as an example, I'm going to show you what it looks like for the sodium atom. So sodium, you look on the periodic table, how many protons does sodium have? It has 11. So I might put 11 down there, although that's redundant, right? That's the atomic number. That's the space that we put that in, which means we have 11 electrons to define, because this is going to be neutral, okay? So I'm going to put a little 0 up here. And so let's describe where those 11 electrons are positioned within the sodium atom using this orbital diagram scheme. And in the orbital diagrams, we're going to use boxes for the orbitals. So we'll have one box here. This will be for the s orbital, the s sublevel. Sorry, let me say that again. The orbital at the s sublevel at n equals 1. If you remember back from the quantum theory, at n equals 1, there's only one sublevel, that's s. And within any given s sublevel, there's only one orbital. That comes, all those rules, right, comes from the solutions to the Schrodinger wave equation. Once we fill up that box with 2 electrons, let's just put them in here. One will be spin up and one will be spin down, okay? Now, if we place the 3rd electron in this atom, there's no more space left at n equals 1, because we filled up the one orbital that's at the one sublevel at n equals 1. So the next electron has to go into the next available energy level. That's going to be at the n equals 2 principal energy level. And if you recall the rules that we went over on Friday, within a given sublevel, they're going to fill in order of S to P to D to F. Now at n equals 2, we only have 2 sublevels. There's an S sublevel and there's a P sublevel. The S sublevel is going to fill in first. And at the S sublevel, there's only one orbital. So we have one box that we're going to label 2s. And the next 2 electrons are going to go in there. Now, by habit, I always put the first one spin up, but it doesn't really matter. I could have put the first one in that box as spin down. What matters is that if there's 2 in the orbital, they're going to have opposite spins, which we arbitrarily will then identify as one is being spin up and the other is being spin down. Right, that places 4. But now the next electron is going to go into the next available energy level. What's the next available energy level after 2s? 2p. And if you review the rules that I very carefully went over with you on Friday, remember we're filling within a given n, that's up here, within a given n, they're going to fill in from S and then P and then D and then F if those are available, okay? So we've got 2p is next. Oh, that's what I meant to show up here. But at 2p, here we are at 2p. When we talk about the number of orbitals, the 3rd quantum number, there's 3 possible numbers now. At the sublevel p, there are 3 orbitals. And I use this idea of taking this lecture hall. This lecture hall is the whole p sublevel. We need to divide it into 3 equal parts. And each part specifies the same energy level, but the electrons in each section are confined to that one section. They don't overlap. There's 3 non-overlapping orbitals that all specify the same energy level. In this case, the energy level is the 2p sublevel. And that's what we call degenerate orbitals. That's the idea there. So in our orbital diagrams now, we show that by having 3 boxes that are all connected. And I'm going to collectively call these are the 2p sublevel orbitals. Now, in some textbooks, they might label one as 2p sub x, 2p sub y, 2p sub z, just to show you that they are mutually exclusive. They're non-overlapping, but they all specify the same energy level. All right, so electron number 5 is going to go into one of these boxes. Now, don't write this down, okay, because I'm about to change it. These 3 boxes are equal energy level. So I can put number 5 here. I could put number 5 here, spin down. Doesn't matter where I put number 5, because there's only one electron that I'm placing right now, and it can be in any one of the 6 positions specified in those 3 degenerate orbitals. Does that make sense? Okay. Okay. Now you can write this down, because by convention, I like to work from left to right. Most of you will work from left to right. And as I already said, by convention, I put the first one spin up. But now you understand that that's really an arbitrary assignment. Now, to place the 6th one, this is where it gets a little mind-bending for you. So I'm going to try to explain this carefully. And what I'm explaining is what we're going to end up defining as Hund's rule. This is all about defining the stablest configuration, the configuration that takes the least amount of energy to keep things the way we're describing them. Given that those 3 boxes are equal energy level, now again, don't write this down, okay? If I put the 6th electron here, what I'm doing is I'm confining those 2 negatively charged electrons to only 1/3 of the available space, okay? It's not that this would never happen, but it's not the lowest possible energy level, because all 3 of those boxes are equal energy level. So by forcing 2 negatively charged things that want to be repelling from each other, right? Negative repels from negative. So it's more stable to put those 2 electrons into 2 separate, non-overlapping orbitals. And the spin's going to be in the same direction as well. That's even more subtle. Right? Things are a little bit more stable when all the magnetic spins are aligned. So I'm going to put that next electron in another empty box, but the spin's going to be in the same orientation. These are what we call unpaired electrons. Okay, so if you have unpaired electrons, they're going to have the same spin. And again, it's arbitrary whether that's spin up or spin down. If I put that first one to spin down, then the next one would be spin down, but it will be in a separate box. Now, when I place number 7, it's going to be the same thing. It's going to be the most stable to put that 7th electron in the empty box, because all 3 boxes specify the same energy level, and the spin will all be the same. Now, there is another orbital here. I'm just going to put it in here. This is now at the next principal energy level, which is n equals 3. And then the first sub-level that we get at n equals 3 will be the s sub-level. So that's the 3s box. But now when I put electron number 8, where's it going to go? Is it going to go in the 3s box, or is it going to go in one of the 2p boxes? It's still going to go in one of the 2p boxes, because following Aufbau principle, the 2p sublevel is a lower energy level than the 3s. So we're still filling in each additional electron in the next available energy level, keeping lowest first before we move up. So now we are going to have 2 electrons in one of these orbitals, but it doesn't matter which one. Again, I work from left to right, so that's fine. But I could have done it this way. That's completely legitimate. I just like working from left to right, okay? But those are equivalent. But what I have to do is, once I double fill that orbital, the electrons have to be opposite spin. And then the next one, and then the next one. This is following Hund's rule. So let me then specify what Hund's rule actually says. When we have degenerate orbitals, And in this case, the degenerate orbitals are the 3p sublevel orbitals, but we'd have the same thing if we were working with the 5d sublevel orbitals, and so on. When we're filling electrons into degenerate orbitals, these are going to be half filled before any of them are completely filled. Or any are doubly filled. Meaning that the only time we're going to double fill one of these orbitals is when all of the degenerate orbitals have one electron in them already. And really, it's just following the Aufbau principle. It's just more subtle. Okay, so now we've placed 2, 4, 6, 8, 10 electrons. We still have one electron left. There's no more room at the 2 n equals 2 principal energy level. All of the sublevels are filled. And to be more specific, all of the orbitals at each sublevel are filled within that principal energy level. So the last electron has to go into the next available energy level, which is a little bit higher. That's going to be the 3s orbital. And again, this one could be spin up or spin down. It doesn't matter, but there's only one left to place. So that's the orbital diagram that describes sodium. Sometimes you'll see this written a little bit abbreviated. I don't know if the textbook does this. I'm just going to show this to you, so in case you see it in other classes, you'll recognize it. But it's really the same thing, except instead of drawing boxes, you have lines. So this would be the 1s orbital. This would be the 2s orbital. And then at 2p, you've got 1, 2, 3. And then you would have the electrons shown like this with half arrows going up and down. That shows the same thing. And notice that this allows us to look at the paired and unpaired electrons. It allows us to see at that level. Okay, so let's just put a little note here. This shows the electrons in orbitals. And that can be useful. The other way that we notate electron placement in an atom is using what we call the electron configuration. And let's again do it for the sodium atoms. So here's sodium, nothing's changed here. Now the notation here is a little easier. We're just going to write down what the principal energy level is and the sublevel, but we're not looking deeper into the sublevel. So we're going to have the 1s sublevel followed by the 2s sublevel, followed by the 2p sublevel, followed by the 3s sublevel. All right, and let me just notate down here. What we're showing here is only the sublevels. But not in their orbitals. And then what we use then is superscripts will tell us the number of electrons present at each sublevel. So at the 1s sublevel, we've got 2 electrons. At the 2s sublevel, we have 2 electrons. At the 2p sublevel, we have 6 electrons. And at the 3s sublevel, we have 1 electron. Okay, so let me just highlight this. The superscripts equals the number of electrons at a sublevel. Okay. So which one you use is dependent on what you want to show with that model. Remember, our symbols and models, they're just describing things that we can't really see. So you use the right symbol or the right model to show what you're trying to talk about. If you care about whether the electrons are paired or unpaired and what orbitals they're in, you'll use the orbital diagram. If you just want to notate overall where the electrons are within the principal energy levels and sublevels, you'll use the electron configuration. Although honestly, for you all, you're going to use whichever one the question asks you to do, right? Just to highlight this a little bit more, let me show you what it would look like, for example, nitrogen. Nitrogen's a little different. How many protons are in nitrogen? 7. So we only have 7 electrons that we need to place. So at the 1s sublevel, well, we're going to have both electrons in there, so we don't need to worry about that. At the 2s sublevel, we're going to have 2 electrons because there's only, that's only 4. We still have 3 more to place. Those 3 are going to be at the 2p sublevel, but we just put a 3 there. This doesn't show where those 3 electrons are. Okay? So you, for example, would have to know that, oh yeah, Hund's rule tells me that those 3 electrons, there's going to be 1 in each of the orbitals. They're all going to be unpaired. And they'll all have the same spin. But you kind of have to know that if you're just working with the electron configuration. If I showed it as an orbital diagram, well, I don't need to write that out. I think you'll see. I think you'll know. Well, sure, let's go ahead and put that in as an orbital diagram. That would be the 1s. That would be the 2s, and then the 2p. And that would look like this. So here, let's do the half arrows because it's a little easier to deal with half arrows. 1, 2, 3, 4, and then 5, 6, 7. Okay? So it's just getting used to that. Now, it would become hopefully obvious in a little bit how else the electron configurations are useful without having to show the orbital diagram boxes, because the number of electrons at a sublevel, how many electrons in nitrogen are at the n equals 2 principal energy level? There's 5. And that's going to become important in a little bit when we start talking about the valence electrons. All right, so just hang on. That's coming up in just a slide or two. In fact, it's coming up right next. Right here it is, valence electrons. So what are those? All right. Well, you can read for yourself on the slide what the valence electrons are. They are the electrons that are in the highest principal energy level that has electrons in them. And I have to emphasize that last little bit, because you can imagine there's all the energy levels available in the atom, but we specify the valence electrons are those electrons that are in the highest principal energy level that has electrons. So in this case, for sodium, how many valence electrons are there in sodium? There's just 1, because 3, n equals 3, is the highest energy level that has electrons in it, and there's only 1 electron there. And you can see that both in the orbital diagram boxes, and you can see it here in the electron configuration, because at n equals 3, there's only the 1 electron. In nitrogen, how many valence electrons are there in nitrogen? There's 5. There's not 3. There's 3 electrons at P, yes, but the valence electrons, you want to look at the number of electrons in the principal energy level. That's going to be both the S and the P, or D or F, depending on what atom you're looking at, okay? And you can read that directly off of the electron configuration. You don't need to count the arrows in the boxes. All right, so it's really important to focus on that, okay? It's the number of electrons. Well, it's the electrons. The valence electrons are those that are in the highest principal energy level. And the reason that we focus so much on valence electrons is because of this other statement that's right here. in all of the chemical reactions that we're going to be studying, it's only the valence electrons that are involved. So everything we're doing for the rest of this semester, all right, when we're moving things around and making bonds and breaking bonds and losing electrons and gaining electrons, it's only the valence electrons that are involved in the chemical reactions that we're studying. So when sodium reacts, it's just that one valence electron that's involved. All those other electrons in the other principal energy levels that are full, they're not involved. Okay. Now, a couple of things to keep in mind here. So valence electrons, as I just said, they're the ones that are involved, and they're going to do one of three things. They're either going to be gained or lost or shared. And they all do that to become more stable. Remember, stability, that's the overriding theme here. If electrons are gained or lost or shared in a chemical reaction, it's because by doing so, the result is a more stable configuration than what we had in the products, in the reactants. Now, we're also going to find that the electrons overall are going to be most stable when the valence shell or the valence level is full. So the valence shell, the valence level, that's going to be, again, that principal energy level, the highest principal energy level that has electrons in it. Things are most stable when it's full. And when it's full, that means that all of the electrons are going to be paired. Right? That's going to specify the lowest energy level necessary to keep all of those electrons stable, the way that we've drawn them out. All right, so why would electrons then be gained? Well, they would be gained to fill up the current level. Or shell. Again, that's a direct result of this statement, because they're most stable if that shell is full. That's going to be the most stable place. So some atoms will gain an electron if they can. They don't just grab it out of thin air, but they'll gain it in the process of doing a chemical reaction with something else that wants to give off electrons. Okay, but the driving force for it is that when it does gain electrons, it fills up completely its highest energy level. That gives us its most stable configuration. For the same reason, electrons would be lost. When they're lost, that allows the atom to, well, for lack of a better word, go down to the previous energy level, which then by definition would be full. Right? Sodium, for example, if I go back to the idea of sodium, sodium has one electron in the valence shell. If it loses that one electron, what's left over? Now you've got the one, n equals 1 is full, and now n equals 2 is full. By losing that last electron, it now leaves itself with whatever the valence shell is. In this case, it would now be 2. It goes down, back down to 2, but 2 is full, and that's more stable. Okay, so that's, again, the same driving force, why it would gain, in this case, why it would lose an electron. All right, it's the same idea. As you'll see, if you don't know already, when electrons are gained or lost, and actually we had an exam question on this, so we did talk about this already. This is what happens when ions are formed, right? If you gain an electron, you're going to form a negatively charged, what do we call those? Anions. And if we lose electrons, that forms positively charged, what do we call those? Cations. Right? These are ions. They are then going to attract. The negative and positive attract. This is going to form our ionic bonds, which we'll study in more detail when we get there in chapter 4. Now, sometimes we'll have atoms where you can't really decide, well, is it going to be more stable if it loses or if it gains electrons? And you'll see that there's a number of atoms that instead of completely losing and completely gaining electrons, they're going to share them instead. And when we share electrons, this then allows both atoms involved in the sharing to have a full valence shell. Whoops. And of course, you already probably know, this is what we call a covalent bond. But now you know a little bit more about some of these terms and understand what the word covalent means. Covalence electrons. They're sharing the valence electrons, right? Covalence, so covalent bonds, the sharing of the valence electrons, so that by the process of sharing, both atoms think that they actually do have full valence shells, even though they're really just sharing some of the electrons. All right, now when they can get their highest energy level full, that's going to bring you, because now you know that you know how the periodic table is structured. All right, that's going to bring you down to the electron configuration of all those elements that are on the right-hand side of the periodic table. What do we call those? All the elements on the right-hand side, the blue column here, the noble gases. Okay. Sometimes the noble gases are called inert gases. Right? These define the most stable configuration. The most stable electron configuration. For a given energy level. Okay, so if we're near neon, for example, if we're oxygen or fluorine, right, we'll probably want to gain some electrons so that we can become most stable the way neon is configured. If we're just beyond neon, like say we're sodium or magnesium, we might want to lose some electrons so that we can, again, take on that electron configuration that's most stable to be like neon. That's also why they're called the inert gases. Inert meaning that they don't tend to react with other things. Because as I've been explaining, the reason that chemical reactions happen is so that the electrons are gained, lost, or shared to become more stable. So if you're already as stable as you can be, there's no motivation to react with anything. So that's why they're inert. Okay, so these ideas now, we're gonna merge all these ideas together to start explaining the electron configurations, and I'll take you through the first couple of periods so you can see how this all fills out. But you'll see as we do this that within a given principal energy level, you'll find that it's the S sublevel that will always fill first. And it will get more complicated as we go on. I'm going to keep it simple at first, okay? But you'll find that at the end of the, well, not the end of the day, when you're describing the electron configurations, you'll find that it's the P sublevel that will always fill last. And again, that's within a principal energy level. So let me just highlight that. So what that gives us, okay, at the S sublevel, how many electrons can we have? 2. And at the p sublevel, how many electrons can we have? 6. So given that s fills first and 6 fills last, this is before we go to the next higher principal energy level. Okay. Before having to go to next n. Okay. That's what I mean by filling first and filling last. This is going to give us 8 electrons. And I'm mentioning that because many of you probably remember hearing something called the octet rule. Okay. And that's kind of where it comes from. This idea of the octet rule, we'll be practicing that in chapter 4 when we start trying to diagram how these molecules are actually arranged. Okay. But this is essentially where it comes from. The octet rule, which, as you'll see later on, is really not so much of a rule as you think it is. Right. So I'll put it in quotation marks. But that's where it comes from, because the overall, the S and P sublevels are full. The valence shell will be full before you move to the next energy level. That's where it's coming from. All right, but like I said, I'm going to try to keep it simple here. So let's now go through both the orbital diagrams and the electron configurations for the first 10 elements. And I'm going to try to take you through this slowly. And while we're doing it, I'm going to emphasize Hund's rule. And I'll try to point out where we have unpaired electrons and paired electrons and where we are the most stable. Okay, so let's just start off slow and then let's see, once you kind of get the hang of it. When we have hydrogen, right, we're going to start with the first proton, hydrogen, 1 electron. So we only need to describe 1 electron. We'll put that in the 1s box. Like I said, by convention, I always go spin up. If I write the electron configuration for that, it would be 1s and then superscript 1, showing that there's 1 electron at the 1s sublevel. Yes, question. I'm sorry, can you say that again? You always have to put the 1 at the end. You mean the superscript 1? Yes, absolutely. The question was, do you always have to put this 1 at the end? And absolutely you do. Because if I just say 1s and without the superscript, that, by the way that symbol works, that tells you that there's no electrons there. Or there could be a 2, right? All right, so for helium, speaking of 2, helium, we're going to have 1 that's spin up and then the other one spin down. So now I'm going to go to the half arrows. And the electron configuration would be 1s2. We don't say 1s superscript 2. We just say 1s2, but you have to kind of know what that means. Now, notice that at n equals 1, we're now full. As I was describing earlier when we were filling out the diagrams for sodium. That third electron for lithium, we always start at the bottom and work our way up. 1, 2, 3. That third electron is now already going in n equals 2 level. So when we work full at n equals 1, that's going to be the most stable. So let's go back over here. This is now full. Now, if I were to add another column here, let's add that right now. Let's follow the valence electrons. I should have had this on your slide for you here. Let's just add another column here. How many valence electrons are there in helium, in hydrogen? There's 1. And how many in helium? 2. Okay, but we're full. This is where we're most stable. I'll also show you there's a condensed electron configuration that we'll use. It's taking the helium atom without specifying it's 1s2. If you see the condensed form like this, that means you've got 2 protons and the 2 electrons in their completed shell. It shows the completed, or it designates the completed valence shells. Designates completed shells. That'll become more useful to you when I go a little bit further. So now let's build up some more. So we go to beryllium with 4 protons, 1, 2, 3, 4. And oh, I didn't put it in was for lithium. So let's do the lithium. That would be 1s2, 2s1. And here, I'll show you how the configuration, the condensed electron configuration would work here. So given that if it's helium, it just looks like that. If I want to show the condensed electron configuration for lithium, it would be the helium core and then 2s1. Okay. For beryllium, this would be 1s2, 2s2, and the condensed form would be the helium core and 2s2. If I now go to boron, 5, 1, 2. Now I'm going to fill these in following Hund's rule. Even though you might know what it's going to look like, always practice filling these in using the Aufbau principle and Hund's rule. Yes, question. The question has to do with why do we have to use the condensed form? You don't have to use the condensed form. I'm just showing you the condensed form, and in a minute I'll show you why it might be useful to you. All right, so follow Aufbau, follow Hund's rule. So I'm following Aufbau. I'm filling them in order of increasing energy levels. And of course, here I don't need to apply Hund's rule yet. That's just 5. 1s2, 2s2, 2p1. And the condensed form is helium 2s2, 2p1. For carbon with 6 protons, 1, 2, 3, 4, and now I can apply Hund's rule. Okay, electron configuration is 1s2, 2s2, 2p2, or if I show it in condensed form, helium 2s2, 2p2. Now let me go back in and fill in the valence electrons. Okay, how many valence electrons are there for lithium? There's just 1. How many for beryllium? 2, 3, 4. So why use the condensed form? Well, the condensed form is nice because, 1, when you get to larger atoms, it saves you a lot to have to write down. But it also then just highlights the valence electrons. So Dylan, maybe that's a better answer to your question. You would use the condensed configuration because it highlights the valence electrons. Everything else that's not involved in chemical reactions, we don't care about. So we just put them in the core of whatever the most stable configuration was underneath it. That's why it's helium, yes. Because helium, if we were to take away all of the valence electrons, what's left? What's the most stable configuration at the one lower energy level? That's going to be the nearest noble gas, or in this case, it's helium. All right, let's continue along here. Nitrogen, I already showed you, so I'll fill that in quick. 1, 2, 3, 4, following Hund's rule. 5, 6, 7. 1s2, 2s2, 2p3. And again, if I just want to highlight the valence electrons, 2s2, 2p3. I don't need to change color for that. Oxygen with 8 electrons, 1, 2, 3, 4, 5, 6, 7. Now I need to go back and double fill one of them. Okay. So with oxygen, look at this. We've got 2 unpaired electrons in oxygen. And you can see that with the orbital diagram. Whoops, 2 unpaired electrons. I want to point that out because later on, when we start looking at the reactivity and how many bonds certain elements might form in chemical reactions, you'll find that it's the unpaired electrons. Those are unstable, okay? Things are most stable when the electrons are all paired up. It kind of says that up here, but let me highlight that. All electrons are paired. But it's really not something that we're going to get into until we get into chapter 4. You'll see that unpaired electrons are very unstable and they're going to want to react. Okay. All right, let's finish our configurations here. 1s2, 2s2, 2p4, helium shell, or helium core rather, 2s2, 2p4, and this now has 6 valence electrons. And you can see them, you can count them, 2, 4 equals 6. Fluorine has 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. We're almost full with fluorine, but not quite. 1s2, 2s2, 2p5. Helium, 2s2, 2p5. It has 7 valence electrons. It's not until we get to neon that everything is full, okay? With 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1s2, 2s2, 2p6. That's now full. So I can write the condensed form 2 different ways. If I want to highlight the valence electrons, I would write it this way. 2s2, 2p6. Or I can just say, now this is the neon core. Because again, that symbol means that it's neon with all of the valence shells full. And that's in fact what neon is, okay? There's 8 valence electrons. We filled up our S sublevel and our P sublevel. We're at 8, we're at our octet. We are now full at n equals 2. This represents the most stable configuration when you have about 10 electrons. So if you have 8 or 9 or 10 or 11 or 12, things are going to happen if they can, so that you can get to this noble gas configuration now for neon. And here's a perfect example of that. Let's go back and take a look at fluorine. Right? Fluorine is almost looking like neon, not quite. Right? Fluorine really wants to get 1 more electron, if it can. Remember, it can't just grab it from thin air. But if fluorine is doing some chemistry with something else that wants to give up electrons, fluorine is going to grab them. Because if fluorine can get 1 more electron, it would fill it in here, if it could. And now we would have fluorine that still has 9 protons. So there's still 9 positive charges. But now it's got an extra electron. Okay, so this now becomes an ion. This becomes the fluoride ion with 1 minus charge. Now we'll cover how we name these, goes from fluorine to fluoride, in chapter 4. This is the fluoride ion. It's going to be more stable than just fluorine alone, okay? But notice that the fluoride ion, in becoming this ion become more stable, it now looks exactly like the electron configuration for neon. You see that? That's the driving force. One second. So there's a new word here, right? The fluoride ion, this is going to be isoelectronic with the neon atom. When we're forming ions. You still have a question? Yeah. So the question was, is that why the elements in group 1A are the most reactive, because they have all unpaired electrons? So, I mean, yes, they are very reactive for that reason. I mean, well, sort of for that reason. They all have 1 unpaired electron. And so if they can get rid of it, like sodium, here, let's just go to that example. Let's just end with this. If we go back and look at sodium now, okay, sodium has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sodium has that extra electron out here, right? And it's unpaired. In this case, it's not going to share it. It's just going to lose it if it can, all right? Instead of looking at fluorine, let's go ahead and look at chlorine, because we all know about sodium and chloride, table salt. So this will be a great example. Chlorine is going to look very much like fluorine, but it's in the next period, right? Chlorine is in period 3. So if we were to draw the electron configuration for chlorine that has 17 electrons, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we're full. This is 1s, 2s, 2p. Now we got to go to 3s. That's 10, 11, 12, and then 3p. 13, 14, 15, 16, 17. There's the 17. Okay. Notice that the valence electrons in chlorine is the same number as the valence electrons in fluorine. Right? These have 7 valence electrons, just like in fluorine. So it's the same argument there. Chlorine would love to get one more ion, and sodium wants to give it up. So it's a match made in heaven. Sodium is going to lose that electron. It still has 11 protons, but now it's going to lose this electron and become the sodium cation, sodium with 1 plus. And if I were to write the electron configuration for that, it would be 1s2, 2s2, 2p6, and that's it. And notice that that's the same as just writing the electron configuration for neon. For chlorine, right, if chlorine gains that electron, now chlorine with its 17 protons is going to have the configuration, well, it's going to pick up one more electron, so it's chlorine minus. This is now going to be 1s2, 2s2, 2p6, 3s2, 3p6 now. What does that look like? That looks like argon. And remember, I could have also written this as the neon core and then just focus on the valence electrons. Okay, so in gaining and losing electrons, we're becoming isoelectronic with the nearest noble gas. All right, this is isoelectronic with neon atom. This one is isoelectronic with the argon atom. It's going to be its nearest noble gas. So this idea of being isoelectronic, it helps us understand why things would gain or lose electrons. So fluorine, chlorine, they're both going to gain one only electron if they can. Same would be true for bromine and iodine. Sodium, if it can, it will lose just one, just like lithium would, or potassium, right? We're going to see that periodicity over and over again. Okay, that's it for today. We'll just continue right along. We're going to get a little more theoretical on Wednesday, but then bring it all back to the same concept.